What I want to continue today is this discussion of stack design and one of the problems we have, particularly in solid oxide fuel cell stacks, of dealing with gradients. No matter what you do, you're dealing with a gradient because we're coming in with fuel that's unreacted and the stuff coming out the back end of the stack is largely reacted. So we have composition gradients, we often have temperature gradients. And so the conditions along the cells or different places within the stack are not the same everywhere. And I talked last time a little bit about some of the consequences of that. These competing effects are kind of going on. They have different relationships. And so you end up with sometimes a fairly complicated current density profile. It's definitely not uniform. And we need to think about integrating that profile in order to really sort out how much cell area we will actually need. So how do we model this kind of situation in a way that we can use for design? One way to think about this, at any point along the cell, as we're flowing stuff along it, we can think of each portion of the cell as being its own, as being a cell. It's a smaller area, but it has a local position, a local concentration, a local temperature. If we were to take a small cell and test it under the exact same conditions we have in the stack, we should see the same current density. So air is coming in here. We've got our fuel coming in here on the other side. Here's our cathode. And here's the anode. So imagine we think about this not as one cell, but think of it as like a whole series of cells that are all connected in parallel. So I'm just discretizing this. It doesn't necessarily have to be uniformly discretized, but we've got m little subcells of different dimensions. They share the same voltage along all of their cathodes. They share the same voltage along all of their anodes. So cell potential is the same for all of them because they're all in parallel. But the current through each little subcell is different. They're small enough that the concentration temperature is roughly uniform within that region. And if they're in co-flow, like I'm describing it here, we can think of this as a one-dimensional variation. If I isolate any one of those cells, I can kind of draw a control volume. You guys have been doing this. You've been doing material balances and energy balances on an SOFC stack. Well, imagine you just take all of that stuff and you just apply it. Instead of applying it to the whole stack, you apply exactly the same idea, but you apply it locally to one slice of this stack of whatever width this is. And you can imagine doing that and you'd have the same material balance equations, you'd have the same energy balance equations. And what would change though is that you're doing it many, many times in series, and then you're coupling all these things together. So what does that look like? Well, the air is coming through this way. So any local position, if I look at what's crossing the control volume, I've got O2 coming in, and I've got N2 going in at some point, and then leaving that same cell, I have O2 coming out and N2 leaving. The N2, of course, has to be the same because it's coming in and coming out and there's nowhere else it can go. But the oxygen can disappear. So oxygen will come in, but less oxygen is going to come out because part of that oxygen is being electrochemically reduced and is being taken through the cell as oxygen ions. And then meanwhile, you can do the same, we can think about the same thing at the anode. We've got hydrogen coming in, we've got H2O coming in as well, because all the cells further upstream were producing water, or maybe you even fed water in. And so these species are going through, and then out, we have some hydrogen left, and we're making more H2O. So H2 concentration H2 flow will be going down because we're going to be oxidizing some of it to water. The H2O flow rate is going to go up from left to right because we're making water and so forth. And then maybe, depending on what type of cell we're running, if this is using reformed hydrocarbons as a fuel, like we've been talking about most recently, then maybe we'd also have some other stuff in here too, to get some CO and some CO2 and some methane. And same thing over here. CO is going to come out, CO2 is going to come out, CH4 is going to come out. Depending on how complicated we want to make our model, they could be, we have some homogeneous reactions that are happening. So water gas shift is happening, steam methane reforming is happening. Depending on the temperature, one of the common assumptions people will make is that we have some catalytic activity within the cell materials. Because we're at high temperature, those reactions come to equilibrium. So we also have some equilibrium relationships. So just as we did with the stack, we had our pre-reformer, we let these gases come to equilibrium, they went in at a state of equilibrium, we partially consumed them, stuff came out the other end, we then redid that equilibrium calculation. Here we would be doing it twice again, one for the inlet and one for the outlet, but this time we're not doing it for a slice of our stack. So same thing again. So we've got material balances. We've got our equilibrium relationships. And then meanwhile, we could also do an energy balance, generate some excess thermal energy that's absorbed mostly by the air. The air gets hotter, and so the temperature going in, we have a T in, and then we have over here a T out. And T out is greater than T in because we're absorbing some of that thermal energy. And so we could do the same thing. We could do an energy balance. Maybe we would constrain the gas flows and then calculate the temperature difference between the inlet and the outlet. Go to the next cell, redo that, go to the next cell, redo that, or try to solve it all simultaneously. One of the things we'll have to come back to and talk about a little bit about is heat transfer. Depending on the solid materials that we have in our stack, the temperature differences that we generate within the stack won't just be in the gas phase, but they'll be in the solids too. And those solids are going to conduct heat. And we actually want that because we're going to generate all this thermal energy in the stack. We would like to be able to redistribute that thermal energy uniformly throughout the stack as easily as possible. And that's to some degree is accomplished by the metal. If you have metal interconnects, they can help dissipate the heat and transfer that heat to the gases, and then the gases can take that heat out. And so also coupled in this is heat transfer. So this sort of gets into the realm of, well, how do you go about doing that? And there are a variety of different approaches to that. One of the most common is finite element calculations. So people will discretize the whole stack into small little tetrahedra and solve the mass and energy balances for each little tetrahedra. And that'll involve fluid mechanics as well. Oftentimes you can incorporate fluid mechanics that way. That's one advantage. Another major advantage is you can incorporate heat transfer. I have colleagues who live and breathe finite element analysis. That's what they do. And they love this stuff. Like you give them a problem like this and they're just like, oh yeah, we've got 4 different coupled partial differential equations in 3 dimensions and these very detailed models that involve all the reforming reactions, and it's totally cool. But you kind of have to be an expert in those methods. Instead, I'm going to be talking about a model that Eric Stuvey is another faculty member in our department, and I have developed starting around the mid-noughts, like 2004, I think was the first version of this, where we used Excel to construct a discretized model literally using cells in our spreadsheet as representations of the positions within the cell as we go across the stack. And then you solve mass and energy balances for each slice. So that's what we're going for. So with these Excel models, we're not trying to be super, ultra accurate, but we are trying to capture the main physical phenomena that are going on while making some assumptions that we can trace and be able to identify where we made those assumptions and, where things are likely to break down in certain circumstances. So we know a little bit about the limits of that model.